So let's start by asking the question about the height of a BST. Everybody knows what a BST is, right? Binary search tree. We also know that there are many shapes for binary search trees. They are defined by this Catalan number that we looked at last Wednesday, right? So, many different shapes. The shape of the tree is determined by what? The shape.
Insertion.
By the sequence of insertions, the order of insertions. Not the keys themselves, the sequence of every tree can be balanced if we insert them in the right order, but we don't always get a choice. And it's very unlikely that the tree will be balanced by itself. So the question becomes, what is the expectation of a tree in terms of its shape? So the question is, what is the analysis for the average height of a BST generated from a random set of n data? So if I have random numbers coming in, the first number that comes in becomes the root. The second one becomes either the left child or the right child. The next one becomes, you know what happens. What do we expect for the average shape? Specifically, we're less interested in the shape of the tree. We're more interested in what? Height of the tree. Why is height more important? Because if the height is close to log, that means it's close to the best. And if it's closer to n, it's close to the worst. So where's the average going to be? Is it n over 2? Is it 3 times log n? What is it? Is the complexity closer to best or closer to worst? So, so we will define the shape of a tree by the sum of the depths of all the nodes in the tree. Okay, guys, you have to shh. We're going to define the shape of the tree by counting the average depths of the tree. Sum of the depths of all the nodes in the tree. Now we know that if the sum of the depths are going to be, for example, if the tree is full, then the bottom level is log 2, and it's n over 2 times log 2. N over 2 is theta n. N over 2 is theta n, so it's n log n is what we're expecting. So if we divide by the number of elements in the tree, which is n, the average depth of a node is going to be log n. But that's the best case, because that's when the tree is full. So the best case is when the tree is full. Half the nodes have a depth of theta log n. Now, I'm just using log base e because theta means proportional. The other half of the nodes have a depth sum, which is less than the sum at the bottom level alone on a full tree. This shows that the sum of the depths of all the nodes is proportional to log n. The worst case is when a binary search tree is formed from an ordered sequence, so that the smallest or largest number is at the root, and each number we add thereafter is either the biggest or smallest value in the BST. In this case, the nodes form a linked list where every node only has a right child, or only left child, or only one child. The nodes of the nodes depth starting at the root going downward is 0 for the root, 1 for the first child, 2, 3, 4, 5, up to n minus 1. And of course, the sum of these depths is theta n squared. So you can see this is the worst case, and then here we have the best case. So where's the average case? So we need to write a recurrence for the sum of the depths of the nodes in an average tree. The recurrence for the sum of the depths of the recurrence of the average tree. So our expression is going to look like this. The depth of n nodes, is going to be equal to, now what we're going to say, it's equally likely that we might have 0 On the left subtree, n minus 1 on the right, 1 and n minus 2, etc., etc., etc. And then we'll divide it by all the n different ways that those left and right subtrees can be split. And so we're going to have the depth of n is going to equal to that plus n minus 1. Now, using the summation, we will get d of n is equal to the sum from the depth of 0 to n minus 1, which is the last depth, di plus d of n minus 1 minus I over n plus n minus 1. This is summation notation. So the question is, does this look familiar?
Yes.
And it looks very familiar. This looks almost the same as our analysis for quicksort average behavior. So what we did was the depth of at n levels is going, with n nodes, is going to be 0 and n minus 1 split, 1 and minus 2, all the possible ways that we can split. And we'll divide it evenly by all the different, by weighing them evenly by dividing by the n possible splits. So what is this n minus 1? This is the question. What is this right here? How do we get the n minus 1? So in equation 5, let's analyze equation 5. In equation 5, we state that the sum of the depths of a tree, of the nodes of a BST with n nodes, is equal to the average, which is a division by n, of its left and right subtrees. If the tree is an average tree in our definition, then the root is equally likely any of the values, so its subtrees are equally likely to be split 0, n minus 1, 1, n minus 2, 2, n minus 3, n minus 3, n. You understand what I'm saying, right? But the question is, where does the n minus 1 term come from? N minus 1.
Cost of splitting.
No. Because we're not doing any work, we're just analyzing a static tree. The n minus 1 term comes from, suppose if di and d of n minus I plus 1 are left and right subtrees of the root. So these are going to be left and right subtrees of the root, right? Then so how many nodes are below the root level? N minus 1. So all n minus 1 nodes are one level deeper in the entire tree than in the depths of themselves. For example, if you look at the left subtree and the right subtree, the left subtree, and this is the root, left subtree, right subtree. If you analyze the left subtree, what's the depth of the root of the subtree? Subtree alone. 0. What's the root of the right subtree? 0. But now we're going to attach them here and here. So these roots now become depth of what? 1. So what do we add? We added 1 to them. So what happens is all the nodes in this left subtree plus all the nodes in the right subtree, there's a total of n minus 1 nodes between the two subtrees because this makes the nth. And all of these, as we attach the root to them, basically they get a depth of plus 1. And that's when we have plus n minus 1. We add 1 to all of the n minus 1 nodes in both subtrees. Does it make sense? I'll go through it again. So each node in each subtree of the root adds 1 to the total depth sum in the tree. Since the root has n minus 1 total nodes between the two subtrees, we add n minus 1. So this is the addition. And of course, we also recognize the fact that when we do this, as we go through the halfway point, we're going to start duplicating things. So what's going to happen is we're going to have the depth of n is going to be twice of this, di. Because the same idea is here. The two d0s are here, two dn minus 1s, two d1s, two dn minus 2s, everything is doubled. So we can do that. So now multiplying both sides by n, which is exactly the same thing as we did for our analysis of quicksort. We multiply them by n. We get this times n. Okay. We also write the formula for n minus 1. So we simply copy the formula exactly as we do. And then we subtract equation 8 from equation 7. And we get 8 minus 7, 8 minus 7. That gives us a lot of disappearing action with our telescopes of our sums. Okay, and then we end up with this. Then we end up with this. Okay, and then if we take the limit of equation number 9, which is this one right here, so this is what we did before, divide both sides by n times n plus 1. So we're going to cancel both of these. If we take the limit of equation 9 as n goes to infinity, equation 9 becomes equation 10, and equation 10 is the same as equation 3. And equation 3 is the one we had for our analysis for quicksort. At this point, we can see that our analysis is going to go exactly to the same place. And the nodes in the average BST, equation 10 is the same as the average of the quicksort analysis in equation 3. Which means that the result is going to be what? 1.38. Remember our number? 1.38 n log n. How many nodes are in our tree? N. So if we divide 1.3 n log n by n, what do we get? 1.3 LGN. So what's that? So what's 1.38 LGN? This is the sum of the depths of an average tree. When I divide it by n, I get what? 1.38 log n, and what does it represent? What does it represent? What does this represent? No, there's no complexity here. We did a shape analysis, tree analysis, right? What is 1.38 n log n represent?
The sum of all the depth.
The sum of all the depths. So if I divide it by n, 1.38 log n will represent what? The average depth. So the average depth of a node is going to be 1.38 log n. What is the average shape of the full tree? What's the theta of that shape, of the depth? Log n. And what's the theta of the average? Log n. So the average binary search tree, its average depth is proportional to the average depth of the best case. Even though the probability of getting a full tree or a balanced tree is so small, it still will be proportional to the best case. So for example, let's think of an example. Suppose we have 1,023 nodes. What's the depth of a full tree of 1,023 nodes?
10.
It's going to be 10. 10. It's going to be LG of 1,024 roughly, right? N plus 1. So that's going to be 10. And what's the average tree with that many nodes going to be? What's the height going to be? $13.8, about 14. Does that make sense? Yeah. So the average is going to be here. So this is the same analysis. They behave, the analysis is exactly the same, but very different problems, but they come out to be exactly the same. Any questions about that? So the average tree tends to be proportional to balance. Yes?
So
Sorry?
you say 13.8,
Yes.
but the height of the tree is 10.
Of the balanced of the full tree. This is the height of the average tree.
Can be skewed.
So the height of the average tree is going to be 13.8. I'm going to round it to 14. Because 13.8 doesn't exist, right? So the average tree of 1,023 nodes will generate a height of around 14. Okay? Does that make sense? What if I had a 2 to the 20th minus 1 nodes? The full tree would have a height of 20, and the average tree about 28, right? It's going to be 20 times 1.4, about 28. So the best case, 20, average case, 28. What's the worst case? A million! The worst case is a million. The best case is 20. The average case, 28. You see how the average case is proportional to the best case. Okay, question, sorry? Okay. That's fine. All right, anything else? Does that make sense what I'm asking? Yes.
I'm reading the first slide and
Which first slide?
like the beginning of
The slide for the tree?
yeah, the beginning, yeah.
Yeah.
No, not that. Oh wait, yeah.
This is the one we started today, right?
Yeah, so that paragraph, like proportional to L and N, I thought it's like N L and N should be true.
Oh, that's what it says. Maybe, could be possible. The other half of the nodes of a depth sum, which is less than the
Last
sum of the
sentence.
bottom. This shows that the sum of the okay. Yes, should be n log n. N log n. The sum of the depths of all nodes is proportional to n log n. Yep. Because the depth is proportional to log n, and there's n of them. So you could say theta n log n, as we did theta here, n squared. So this is the worst case. This is n log n was the best case, and the average case is right there. Okay? All right, so it's a very interesting result. So that tells us, now, there are a lot of very interesting algorithms to keep trees balanced. I don't know how much time I'm going to have to cover them. There are some interesting trees called red and black trees. There are AVL trees, B trees we're going to cover. All of them tend to keep trees balanced all the time. But in order to do that, they require extra work. So there's extra cost to keeping trees balanced all the time. But the question becomes, if your data is coming in random, is it worthwhile since the average case is going to be close to the best case? And the answer is, if you can guarantee that the data is coming in randomly, it may not be a good idea. But if you cannot, then you could have these horrible trees that basically get very skewed. And that would be a problem. Okay, so that's it for that. All right, so let's go to the next interesting thing. So now we're going to look at another algorithm. So this algorithm we're going to look at is, we're going to look at a few algorithms that have to deal with string processing, string searching, string matching, etc., string generating. So string is a sequence of characters, right? So we're going to look at something called LCS, which is the longest common sequence. Now, there's a reason we're going to study this algorithm. It's a very interesting algorithm, and it's an algorithm that we're going to solve by recursion first, but then we're going to find a better way to solve it, more efficient. So this is the reason why we're covering this one. So LCS. So if you look at this, notice that there's a string of characters A, B, C, and D. Same thing here. And what we're looking for is we want to match. See how A is matched to this A? Once I match A to A, I can no longer match this or this to anything else. And then I match this D to D and this B to B. Notice that A, D, B, B, A, D, B, B occurs as a substring in the same order, top and bottom. And we're looking for the longest substring that appears on both strings, the longest one. So for example, you could just match, for example, B to B. That would be a single character. Or you could match CB. But notice we can extend it further. Also, we're interested in, is there a 6-character string that can be matched? For example, this B, maybe it's better to match this B to here. Because if you match this B to here, then you could still get a C and you could still get a B, but that would be only 4. So the point being, if these are pretty long strings, it would be very hard to see what was the longest common substring. So the substring means that the characters on the substring occur someplace in the same sequence within the string. Not in order, but someplace in the sequence. Now, What we're going to do is we're going to solve this recursively, but then we're going to look at another technique called the table-driven algorithm. And a table-driven algorithm is a way we can solve an algorithm using a table. The table can be either a vector, which is a linear matrix, just a one-dimensional matrix, or it could be a two-dimensional matrix, or it could be a three-dimensional matrix. It's some type of a table. One-dimensional, you can have two-dimensional, you can have three-dimensional tables, and beyond, I suppose. So now we're going to define x and y as an elements of a string. So x and y are strings, and we'll define p and q as characters where they're different. So p is a character, q is a character. They're variables that represent characters. So p could be anything, q could be anything. But we're saying if p is a character and q is representing a character, they're different characters. So the only way that p is matching something is p and p will match. Q and q will match, but p and q will always mismatch. So we're going to say if x and y are strings, the longest common sequence of a string x and an empty string is the empty string. Does that make sense? Because there's nothing here. And the same token, empty string and another string y also is nothing. But if you have the LCS of the character p followed by the string x and the character p followed by the string y, then p matches p as a single character. Therefore, LCS of px, py is p followed by the LCS of xy. Does that make sense? Okay. And if we have the LCS of p, x, and qy, suppose that p and q are the first characters of x and q is the first character of y. Do they match? No. So therefore, the LCS of px, qy is the LCS of x, qy, or LCS of px, y. Does that make sense? The first characters do not match, so we don't have this match. First character to first character. So therefore what we're going to do is we're going to strip off the first character, p, and just take x, which is the remainder of the string, with all of qy. Or we can take the first character of y, qy, which is q, and just match y with px. So the longest common sequence between px and qy will be either this, without the p on the first one, or without q on the second one. Does that make sense? Because they're not matching. So therefore we cannot match p to q, so therefore we will match p to maybe the first character of y. Or maybe we'll match q to the first character of x, or something like that, if it exists. Are you with me? Okay. Any questions?
Sir,
Yeah.
could you just explain how that thing is working, that those two sequences x and y? I'm a little confused how the substring is working over there. Like
Okay, so x is a string, which is a sequence of characters. Y is another string. But p and q represent a single character. Okay, that's why if we had px, that means it's a single character followed by a bunch of characters. Py, same character followed by some other characters. So clearly, if p is matching p, then the longest common sequence will include one character followed by the longest common sequence of the remaining characters beyond the match. For example, if you have funny, funny, and furry, furry, then the f's match. So the longest common sequence starts with 1 plus whatever is the LCS of Ani and Azif. Notice that in each case, if we have funny here and fuzzy here, that we are pointing at the F and the F. So now, as we match them, both of these guys are moving forward. But as they both move forward, it's a match, so we add 1 to the LCS. And now we have to find out whether UNNY and URRY. And you can see FU matches. F matches, UU matches. Then you have NNY, RRY. N does not match anywhere. This N does not match anywhere. R doesn't match anywhere. But the two Y's will match. And I'm getting 3. It's a simple example, but you'll see more complicated versions. Does that help? Okay. Okay. So now, let's just look at some of the values here, the examples here. So what we're going to say, if we do the complexity analysis of LCS, we'll say that if the length of x, the length of the string x is n, and the length of string y is m, then W, which is the worst case analysis of W, 1m, that means that's the worst case analysis of a string of length 1 with a string of length m, which is in this case y, is m. Because what we're doing is we're basically checking if this one character in x matches any of the characters in m. If it does, good, but it might not. So therefore we may have to check all of them. So W1m is m, and Wn1 is n. So that leads us to this recurrence for the worst case. The recurrence for the worst case is Wnm. So that's the worst case analysis of the first string having a length of n, and the second string having the length of m. So therefore the worst of nm is going to be the worst of nm minus 1 plus the worst of n minus 1 m. Why is it the worst case?
Because we're having to match all the n with...
Why is it the worst case?
No match.
No match. And so if there's no match, then you can see that we will never match n, the first character here with this first character here. It's the worst case. We never match anything. But we're always checking anyway, right? Checking everything because we can have a match anywhere. We work just as hard to find no success as we do to find success. We work just as hard. But we just don't get success in the worst case. So that's why we're saying, so does everybody understand how this is working? Any questions about that? This is the case where the first two characters don't match. So this is the case of px and qy, and this is x. Sorry, this is px and y, and this is x and qy. You understand that, right? Same as before, but now we're doing this numerically. Now, of course, n minus 1m is higher complexity than n minus 1, n minus 1. And m minus 1 is also higher complexity than n minus 1 because this one is 1 less than this one, and same here. This one is 1 less here, and same here. So therefore what we're going to do is, because they're so close, we're going to basically go to n minus 1 and m minus 1, double it. Since we know that's a little bit less, we know that this complexity will be a little bit higher, or could be greater than or equal to this one. Does that make sense? So therefore we have t of nm is equal to 2 times t, or w of nm is greater than or equal to 2w n minus 1 m minus 1. So what's happening from our recurrence standpoint is that we have these n and m coming in, okay, and then we have 2 times n minus 1, m minus 1, this way and this way, is branching twice. So we can kind of draw a recurrence tree for that, right? Analysis. All right. So if we do this recurrence, we get w of nm is greater than 2w n minus 1, the same thing we had before. And if we repeat this, well, that's too big. If we repeat this I times, we're going to WNM is going to be, look what's going to happen, right? 2 times 2 times 2 times 2 times 2, 2 times 2, n minus I, m minus I, which is going to be 2 to the I times W of this one. Now, the two string lengths, m and n, may be the same, or one of them may be shorter. We're going to assume one is shorter than the other. So suppose that m is less than m. then we will let I equal to n minus 1. Then the worst case WNM is going to be equal to 2 to the n minus 1 times W of 1 m minus n plus 1, which is just going to equal to m minus n plus 1 times 2 to the n minus 1. So this is exponential, right? Exponential in n, where n is the smaller of the two strings. So if one string is 10, the other string is 50, this is going to be 2 to the 10th, or maybe 2 to the 9th. And this is m minus n plus 1. This is what? This is the number of characters that the longer string is longer than the first string. M minus n plus 1.
Excuse me, Professor.
Yeah.
We're saying it's n minus 1, so basically we're taking the shorter one so that it doesn't generate a negative. But then as a result,
Correct.
aren't we leaving a part of the m, a wider part of the m? Because m is greater than n, right?
Yes.
So,
N is smaller, right?
yeah.
M is greater. So what we do, you saw how we solved it, right? So we repeat this.
Yeah, but we're leaving more part of the m unresolved than n.
Well, we could also say they're both the same. We could both the same, which is fine. If both the same, then we can still let I equal to n minus 1. Right?
Yeah, definitely.
Because then they're both going to go down to single. Okay, so we already know that W of 1 and something else is just going to be something else. So W of this is just going to be this times 2 to the n minus 1, which is exponential. So it's an so if we have, for example, a string is 10 and 12, that's going to be 12 minus 10 is what? 2 plus 1, 3. So it's going to be 3 times 2 to the n minus 1. If the strings are the same length, then we're going to have this minus this is going to be 0, and you're just going to get 2 to the n. And 2 to the n will be the length of either of the two strings. So the complexity is exponential. So would you say that's the theta of the algorithm, big O of the algorithm, little o? What's the best one? What's the best letter to stick in front of this? Now, keep in mind that m minus n is a tricky thing. Okay? Because let's say the short string is 25 characters, but the longer string is 5 million characters. Then this coefficient becomes extremely huge. If you're looking for the longest common sequence from a word like this inside of a book. So it could be quite complex. It would take a very, very long time. So therefore, you have to keep in mind to the fact that this is an exponential complexity of the shorter of the length of the strings or the length of the equal strings. But this is this a constant or is this still a variable? You can kind of look at it both ways. It depends on your application. Like I said, if it's 5 million and this is 20, then it becomes very, very complex, right? This becomes a huge coefficient, so the algorithm, which is exponential, becomes much worse than that. You know what I'm saying? It becomes 2 to the 10th times many millions. So it's not quite a constant here. But if we're searching for strings that are approximately the same length, then we can say this is a constant. See what I'm saying? All right. Okay, so let's solve. So we solved the recurrence. So if we think of the strings being similar sizes, and we think of this as a constant, we would say this algorithm is exponential in the length of the shorter string. Would you agree with that? Or if the strings are close together, we would just say it's exponential in the length of the string. Okay? It's going to be 2 to the n. But if m is just 3 more, then it's going to be 2 to the, still going to be exponential of 2. However, this algorithm is, so we can say it's definitely, if this is a constant, this is definitely big O of 2 to the n. but it is not theta of 2 to the n. Well, this algorithm is, but we can actually do this algorithm in much better efficiency using a different approach. Specifically, I told you we're going to use a table-driven approach. Okay, so let's take a look at implementation of this algorithm just for fun. So what we have is we're going to try to look at the LCS, inefficient recursive algorithm. And so we're looking for LCS of ij. Precondition is x and y are global strings. So x and y are global strings. They're indexed 1 to n and 1 to m respectively. And the postcondition is that LCS returns the length of the longest common sequence. Look at the logic we have here. So table ij will be the value of the ith character of the first string against the jth character of the second string. So when I is equal to 1 and j is equal to 1, we're comparing the first characters of both strings. So ij is an entry, okay? So what we're going to do is we're going to put values inside those table ij's so that table sub n sub m will contain, will be the biggest index on both m and n, that will contain the length of the LCS. Okay, so a table is really a two-dimensional structure. So a table is a two-dimensional structure. Okay, so we have the first string going down this way, and the second string going this way. So we have 1 to n, 1 to m. So the index n, m is this index. That's the deepest index. That basically compares the last character of the first one to the last character of this one. And inside this square will be the count of the LCS result, the length of the longest common substring LCS. Okay, so now what we're going to do, we're also going to do one more thing. We're going to, so if we have 1 to n for the first string, our table is going to go from 0 to n. And if it's 1 to m on the second string, we're going to go from 0 to m. So we're going to allow an extra row and an extra column, which we're going to call column 0. And we're going to always assume the column 0 is going to be 0. Because 0 represents the character before the first character, you cannot possibly match on it. So the matrix will be an n by m matrix with an extra row and an extra column, all of which are zeros. Because think about it, you're comparing the 0th character against anything, you're going to get a 0. And same thing here. So, LCS ij, if table ij is empty, that means we haven't set it yet. If I is 0 or if j is 0, if you are in the 0th row or the 0th column, then set it to 0. Okay? Else, if xi is equal to yj, if the ith and j characters of the two strings are equal, then table sub ij will be equal to 1 plus the LCS of I minus 1, j minus 1. Notice that this is a recursive call. But forget about the fact that it's a recursive call. What's the interpretation of that? The interpretation is let's suppose that I have two strings. And I'm looking for the first string, I'm going to look at character 3, and this is character 7. Character 3 and character 7. I is 3, j is 7. I just got a condition x3 is equal to y7. True, they're matching, right? So whatever was the value of LCS before that, I just have an extra value here, right? Are you with me? So I'm matching character 3 to character 7. They cannot be matched again against each other. So therefore the value of the LCS at position 3, 7 is the value of the LCS at position 2, 6. Because 2, 6 contains the LCS of the first 2 of the first string against the first 6 of the second string. So therefore, my table ij will be 1 plus the LCS of everything but the current match on the first string, everything but the current match on the second string. Does that make sense? Furthermore, if these characters do not match, then table ij will get the max of LCS I minus 1j, comma LCS I j minus 1. If character 3 is not equal to character 7, then the value I'm going to put into the table, and I am going to put a value into a table, is going to be what? It's the maximum of I minus 1j. What's that going to be? I minus 1j, whatever it was up to that point, because this is not a match, so what did you get up to this point?
7.
And maybe I'll do this one and here.
3, 6.
So whichever one is the greater of those two, that's what's going to go here, because the greater of the mismatch, taking one character out or the other character out, is what I want at this point. Because I'm not going to put a 0, because the LCS is accumulating a value. So now, this algorithm is quite intense, if you think about it, because basically if you have the strings, let's say you have the string, let's say you have the string under and the string uber. So under and uber. Okay. UNDER 5, UBER 4. Under and uber. If I did an LCS of under uber, I would go LCS 5, 4. This would recursively solve the problem. Because what would happen is, what's I and J? I and J would be equal to 5 and 4. The condition is true. Therefore, table ij, table position 5, 4 is 1, because it's a match, plus the LCS of, get the idea? Okay. I'll show you a better picture of that, but you get the idea. So that's a recursive approach. This is sort of an idea of what we would look at. This is not a perfect diagram. I think I made some mistakes on it, but the idea is pretty simple. So here we have acorn and car. Acorn and car. So we don't match, but we have a length of 5 and a length of 3. So because it's not a match, we get 4 and 3 and 5 and 2. You get it? And we continue going on and on and on down. So this is the way the recursion would look. Now, when we're talking about a table is usually, not always, but usually two-dimensional. Sometimes one-dimensional, but it could be more than that. What we have here is we have something in this table-driven algorithm that is known as a topological ordering. A topological ordering means that there is an order to where the square is inside of the table. In this case, a two-dimensional table. And what we're seeing here is that the topological order for LCS, if we were to put it into a table, think about it. This is, so how many letter word is it going across?
4.
3. And how many is going down? 3. Why do I have 4? I need those zeros. Okay, so everything here is going to be 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so what's going to happen is LCSIJ. It means this one right here. If I match here, that means the first word on the second character matches the second word on the second character. That means the LCS is going to be equal to 1 plus whatever was the LCS here. Does that make sense? The matching on the second character in both has 1 plus whatever was on the first character in both. If you mismatch on the second characters, that's a 0 plus whatever you had here or here, the greater of the two. If you mismatch on the second characters, it's still possible that you might have had what? A match with the first character here, or a match with this character here. So if this is a 1 and this is a 0, you get a 1. Because you're accumulating the value of the LCS. You're not computing it. You're just accumulating it. For example, suppose the value here is 2. What does that mean? What does a 2 mean here? A 2 means that 2 means basically I compared the second character against the second character. The only way I'm going to get a 2 there is if the first characters match and the second characters match. So if I get a 2 here, what's going to go here? Could it be a 1? Could it be a 1? Yes or no? Could it be a 2?
Yes.
When? If they don't match. Could it be a 3? When? Okay, if they match. Now suppose, forget about everything I said. Now let's go back in here. Suppose this is a 1. What does that mean? Suppose this one ends up as a 1. That means one character is the longest common sequence. That means maybe there's a single letter in 1, 2, 3 that matches somewhere in the other 1, 2, 3, but only a single one. Does it mean that there's only one letter in common? Yes or no? Yes. However, there may be more than one longest common sequence of order 1. For example, imagine that we have the following string. The first string is cat, C-A-T. C-A-T. The next string is A-A-A. What's the value here? What's the values here? Zeros. What's the value here? C against C, cat, C-A-T, A-A-A. What's C against A? 0. Plus whatever's here. 0. Now, how about this one right here? What character am I matching? So this is cat, A-A-A. A against A. What goes here? 1 plus the max of this and this. So it's going to be 1. What's over here? T and A. What's going to go here?
0 plus 1, 1.
It's going to be 1 because it's going to be 0 plus the max of here and here. Max was 1. It's going to be 1. Now I'm going to go over here. What's the character here? So what I'm saying to you is the CAT, the A in cat, the A will match here, here, and here. But it's not going to be additive. It's never going to be additive. So you end up with a 1 here. Okay, so looking at this, what we can see is that if I want to compute this, all I need to know is this, this, and this. If I need to know this, all I need is this, this, and this. If I need this, I need these 3. This shows the topological ordering. So what's the complexity of implementing this algorithm this way? Look at the table and tell me what's the complexity of filling in this table, because filling in this table is paramount to solving the problem. What's the complexity of filling in these guys? N plus M? Minus 1. Okay, so now, after I fill in the row 0 and the column 0, can I fill in this? What's the complexity of filling in this cell? Theta? Theta? Say it. 1. What's the complexity of filling in this cell? Can I fill in this cell right now? Yes, because I have this one, I have this one, and I have this one. So, what's the complexity? How about this? How about this? Okay, so what's the complexity of filling in the whole table? Well, a correct answer might be n squared, but it's not n by n, it's n by m. Or specifically n plus 1 by m minus n plus 1. But really, we call it, how about nm? Theta nm. What kind of complexity is that if the two sides are proportional? If the two strings are about the same, if the two strings both have 30 characters, or 30, 32, it's about n squared. So that's a lot better than exponential. So we now know that this algorithm has actually an n squared complexity where n, or we could say big O of n, where n is the longer string, or big O, or big theta of mn, so we don't care which one is the longer or shorter, or big O of n squared if they're approximately the same. Okay, so you see what's going to happen here? So these are all the zeros that we're going to fill in, and that's how it's going to work. Okay, so let's take a look at an example because you guys are a little lost to me. So here we go. So here's an example. Okay, so here we go. So here is, do you see this word? Fair. Carpet. Okay, so these are filled in automatically. Then this is a comparison of F against C. It's a 0. Therefore, it's going to be 0 plus whatever was at, this is 1 against 1. It's 0 plus 0 against 0. Now this is A against, so it's going to be 0 plus max of this and this. When we go this, that means 1 shorter on the second string, the same length on the first string. When we go up, that means 1 shorter on the first string, the same length on the second string. Okay, so that's 0. That's R against C, 0 plus max of this, 0. E against C, 0 plus max against 0. Now we're going to go here. F against A, 0 and 0. So it's going to be 0, 0 plus 0. Now we have A against A. A against A. That means we're taking this character and this character. It's a match. So it's going to be 1 plus whatever you matched at. So this is a match on 2, 2 plus 1, 1. Whatever you accumulated at 1, 1, it's going to be that much plus this extra match. Now we're comparing which characters? R and A, is it a match? No. So therefore, FAR to CA takes this one because we had a 1 FA to CA, so FAR to CA is still 1. So we take the max here and here, it's a 1. Now we're comparing E against A, not a match, but when we compare E against A, it's really comparing the LCS and FARE against CA, and it's still 1. So we take the max here and here. When it is a mismatch, we go up and over max. When it's a match, we go 1 plus diagonal because both characters are being used up. Here only one character is being used up. Here's in the first string and this one in the second string. First string, second string. Get it? So that's how this row gets filled in. Here we're comparing A against R. Not a match. But this is really FA against car. And that's 1 because this is 1 and this is 0, so we take a 1. Now here we have R against R. That's a match. So it's going to be 1 plus whatever you had. So car, R to R is 1 plus LCS of fa and ka. That's why it's a 2. This is a 2 because the mismatch carries down the max. 2 against 1 is a 2. 0. This is a 1 because max on a mismatch of A to P. R to P, we take max. E to P, we take 2 because max of 2 and 2 is 2. We come down here. F against E, 0. So F against E means that the string F and the string CARPE have 0 LCS. It's true. So here we're going to have A against E. It's not a match, but we take this one. Here we have R against E. It's not a match, so we take the 2. Here we have E against E. That's a match, so we take 1 plus. Diagonal is 3. Finally, by the time we get here, it's not a match, but we get the max here, which is going to be here. So the LCS, the LCS occurs in FARE, CARPE, and the T doesn't add us anything. All right? All right, I'm done. Sorry. All right, I'm gonna call it class. All right, see you on Wednesday.